So on this assignment, I guess it was remote because of the hurricane? Is that why it was remote?
Yeah.
Okay. So you were supposed to look up the data sheet for the 74LS08 chip available under lab resources in the course Moodle site, and what type of chip is it? So I'm going to do the same thing, the same questions that were on here, but for a different chip, because I can't do your exact lab for you, but it's almost as good. So the chip I'm going to do is the 74, I believe it's the 74LS32. And the way I find it is I go to the Moodle site and I go to lab resources, and you have the data sheet for chips, and you'll download that. It'll be a zip file, and then you unzip it.
The one for our lab is 74LS08.
I believe so, yeah. And then you'll have a folder, after you unzip it, you'll have a folder called Data Sheets. And you'll go in there, so yours will be 74LS08. The one I'm doing is 74LS32. So we'll open up the one you're going to do, because that's not telling y'all too much. So the one that y'all are going to do is, and y'all just tell me if something's not showing up on the screen, because this is my first time trying to do this with 2 screens. 3 screens, really. So y'all's is the quadruple 2 input positive AND gate. So for the question that says what kind is it, that's the answer to that question. But I wanted to do the 32. And you'll see that I'm doing the quadruple 2 input positive OR gate. So not that different. So for mine, the answer to the first question is that this is a quadruple 2 input positive OR gate. All right, so let's see. The next thing that we want to look at is he has posted on the website a sample data sheet, so you can see what the various parts of the data sheet are. So if you go to the, oh, and by the way, while I'm here, if you look under SI resources, this is where I'm going to post any videos that I do or any worksheets that I have will be right here. So under lab resources, we'll go to sample data sheet with comments.
Just cut that cover.
Oh, good, okay. Sample data sheet with comments, download that. And then open it up. Okay, and so it'll tell you, you don't know yet, because y'all have y'all had a physical lab yet?
No.
Okay, so you're gonna have your first physical lab tomorrow. So I wish I should have brought them to show you. So what these are, they're little things about half the size, about a little bit smaller than a domino. Y'all? Yeah, a little bit, and they have pins on them, and you're going to plug them into a board, and you're just going to push those pins down into the board. And those pins are what these labels are here, and so that's how they're labeled, except they're not going to be labeled on the chip itself. That's why you need this data sheet to know what the pins are. And so the ones that y'all have in the lab are always going to be this, I think will always be this top package. They're always going to look like that. Yeah, I don't have any in my office to show you, but that's what they look like. And the pin numbers, if you look down here, 1, 2, 3, 4, 5, 6, 7, and then starts on the other side, 8, 9, 10, 11, 12, 13, 14, those are the pin numbers. And then the inputs are listed on the side, and that's the algebraic inputs. And then it shows also a circuit diagram, and so this is showing, oh, I'm doing the wrong one. I'm doing the one that's y'all's assignment, right? Yeah. Oh, no, this is just a sample. Yeah, this is just the sample. So it's showing that this is a NAND gate. Y'all probably haven't done a NAND gate yet. So it's just showing a NAND gate, and it's showing the two inputs, 1A and 1B, and the output 1Y. And we'll see how that works later. And then on page 3, you have the input that you'll need, except I just moved it. And it shows the propagation delay. So what that means is a signal comes into the chip, and you're doing digital logic, so signals are either 0 or 1, and they can change from 0 to 1. And as the chip, it takes a certain amount of time for that change to register. And so what this is showing you, the top line is the propagation delay when the output changes from low to high. So when the signal goes from 0 to 1, or that's high voltage or low voltage to high voltage, then that's you have the typical amount of time that it takes, and you have the minimum amount of time that it takes that's shown here. And I believe those are in nanoseconds. Yeah, units, nanoseconds. Units are right there in nanoseconds. And so the typical value, the typical amount of time it would take is 11 nanoseconds, and the maximum is 22 nanoseconds. So that's just showing on the sample data sheet. On the one that I was going to do, so let me close this. And let me see what the questions were. Okay, so look up the data sheet. What type of chip is it? Show the truth table for our logic gate and the 74LS08. So we're going to do a truth table for the 74LS32. So X1, X2.
You grab a chair, so like right here on top of the Alright.
And anytime you make a truth table, if you have just two variables, then you have four possibilities. You could have them both be 0, or you could have the first one 0 and the second one 1, or you could have the first one 1 and the second one 0, or you could have them both 1. So your truth table is going to start out looking just like this, and then on my data sheet, so the one that I have, which is a positive OR gate, if I scroll down, it tells me right here it has a function table for each gate, and H stands for high and L stands for low. And that's actually a little bit different than 0 and 1, because you have some chips that are backwards that you'll learn it's one way in digital logic, and then the chip will say it's I forget how they define it, but it's like it operates going with the way I would think of it, with zeros acting as ones and one acting as zeros. So this one, but for right now, we can just think of high as 1 and low as 0. So what this is saying is if input A is high and B is anything, then our output is high. So that tells me that when input A is 1, no matter what B is, 1 is my output. So that's what that means. And then it says when input B is high and A is anything, then my output is also high. So that would be this one. And then it tells me that if both inputs are low, my output is low, and that corresponds to 0. So that would be my truth table. So you'll do your truth table the same way based on the function table that's on your data sheet. Okay, and then the next question says, suppose you have a 74L SO8 chip on a breadboard, such as on a trainer kit in the lab, and you have access to all the pins on the chip. Explain how you can verify that this chip is working correctly. Okay, so this is going to be hard since you haven't had a lab yet, but I will explain to you how it would work. So you would put your chip, you're going to put your chip on the breadboard, and we saw that on our data sheet it was 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10. So it was they're always numbered like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and you'll see that they're always have. I did that side wrong, right? Yeah, I did. 1 is at top. I knew that.
I have a question.
Sure.
So wait, so the high means 1 and the low means 0?
Yes.
Okay,
Yeah. Okay. And pin 7 is always ground. And pin 14 is always labeled VCC. That means you're going to connect it to the high voltage. And your lab TA will show you this. But so you're going to connect you're going to connect pin 7. That's going to be connected to ground. And when you get to lab, your lab TA will show you that. And pin 14, you're going to connect that to VCC or the high voltage. So you're always going to do that. So to answer this, the first thing you would say would be you would connect, and the way you're going to do that is, I don't think I have a breadboard in my office. Let me show you what one looks like. Okay, so this is a breadboard over here, and what you're going to do is you're going to put your little chip, it's going to go across these, and you're going to attach ground to one of these vertical lines, one of these vertical channels, and you'll attach the high voltage or VCC to one of these. And then pin 7, let me just grab a picture of this. And you're going to learn all this in lab tomorrow, so you don't have to worry about understanding it too much. So you're going to put your chip is going to be right here. And the pins on the chip are going to plug into these little holes on the breadboard. And let's say you have ground attached to this one of these holes right here. All of these holes are connected, and all of the holes on a row are connected. So all of these are connected. So if you attach to any one of them, you're attached to that pin. So if this is pin 7, I put a wire in here, and then I put another wire in there, and then that makes it ground. And then I'll put a wire here for pin 14 and a wire here into the high voltage, and that'll make it high voltage. And I will have attached, it's probably 5 volts is what you'll have it set at. I'll have that attached right there. Okay, so that's what that would be. So you'd say connect pin 7 to ground and pin 14 to VCC. Then connect pins. So let's see which pins were inputs. So when we look at this package, our inputs were A's and B's and our outputs were Y. So anything that's an A or a B is an input, and anything that's a Y is an output. So 1 and 2 are inputs because 1A and 1B. 4 and 5 are inputs. Y'all help me remember this. 1, 2, 4, 5, 9, 10, 12, 13. So yours will probably be real similar, since mine is an OR gate and yours is an AND gate. Yours is probably be very similar to this. So then connect pins 1, 2, 4, 5, 9, 10, 12, and 13 to switches. So you're going to have this thing called a trainer kit that has switches on it. When you connect them to switches, those switches will correspond to on or off, or 1 or 0. So then that means you can either send it a signal of 1 or leave it off, and it'll be a signal of if it's off, it'll be a signal of 0. And then you'll connect pins 3, 6, 8, and 11 to, since you haven't done this before, you don't know what you'll have available. So you can just say like some sort of monitor. So you have little lights on there. You can just say you could connect it to an LED. And so what that would mean is now you have it all set up. So now you know you've got switches attached to each input, and you've got a light attached to each output. So since A equals 1 and B equals 1 corresponds to Y equals 1, when both switches are on, the LED should light up, because we had our truth table said if they were both on, our output is on. And for the OR gate, it doesn't have to be both of them on, it just has to be one of them on. So if either one of them is on, that's not going to be the same for y'all's. So you would not, this next sentence I'm going to write is not going to be true. So you'd say, for mine, I would say if either if either A or B is on, the LED should light up. But if both are off, the LED will go off. And let me get you a picture of what I'm talking about. Okay, so you'll have something that looks like this. It might even be this one. And I have one. I just don't have it in my office right now. But if you ever need to make up a lab or something, you can always come to my office because I'll try to remember to bring the stuff here. And so here's the breadboard. So you'd attach the breadboard here. No, this is not the one they have in the lab. I don't see where the switches are on this one. But you would connect a pin to... Let me see if I find one that looks more like I'm familiar with. It's the same one I just had. Okay, well, anyway, you would attach the pins. Oh, here are the switches right here, the logic switches. Okay, so if, let's say you have the chip in right here, you would attach pins 1, pin 1 to switch S1, pin 2 to switch S2, and pin 3 to an output that would be on here somewhere, and then you can just flip the switches and see if it operates according to the logic table. Does that make sense? Okay. All right. And then let's see what's next on your lab. Okay, with input x1 equals 0, draw a timing diagram showing x1, x2, and y as x2 changes from 0 to 1. Okay. x1 equal to 0. So it says x1 equal to 0, so I'll have x1 equal to 0. And then x2, it says changes from 0 to 1. Zero to 1 to 0 to 1. Okay, so x2 goes from 0 to 1 to 0 to 1. And then I look at my truth table to see what y does. And in my truth table, it says if x1 and x2 are both 0, y is 0. It says if x2 is 1 and y is 0, y is 1. And then here it says if they're both 0, it's 0. And then here, if x2 is 1 and x1 is 0, it's 1. So that would be my timing diagram in this instance for an OR chip. It's not going to be what you'll have for an AND chip. Y'all talked about ORs and ANDs? Yeah. Okay. So now it says this time I'm going to make x1 equal to 1, and I'll do the same thing. Okay, so now x2 is going from 0 to 1 to 0 to 1. And this time, my output is going to be 1 the entire time because x1 is always 1. And my truth table for the OR chip says if either one of them is 1, my output is 1. So that's what my timing diagram would look like for in that instance. And then the next question, use the switching characteristics table. What is the typical propagation delay when y changes from 0 to 1, when it changes from 1 to 0? Okay. So I want to go to page 3. And on page 3, is this page 3? That's page 4. Page 3. So page 3, this one says from low to high. So from the top one is from low to high. From low to high, the typical time is 10 nanoseconds, and the max time is 15 nanoseconds. So what was the typical time? 10? Yeah, it's not going to be the same for y'all's. So mine was 10 and 15. And from 1 to 0, that's high to low, it's 14 and 22. And y'all's will be different from that. Okay, and then it says draw a circuit with logic gates for that function. Your circuit should have 2 AND gates and 2 NOT gates. Let's do one with 2 OR gates and 2 NOT gates. Okay, so this is the circuit I want to draw. And so first I'm going to draw my circuit diagram. So I have 3 inputs, A, B, and C. And by the way, I'm going to try, but my circuit diagrams are usually quite messy. And for A, I want not A, and for C, I want not C. So I'm going to put in a not gate. And then I want the OR of not A and B. And then I want the OR of that output and that function was called Y. Okay, so now we're supposed to map that to our chips. And so if you look here, we have, so that was the circuit. Map your logic circuit to IC chips, see the appendix. Use one SL08 chip with 2 input AND gates and one S74 LS04 chip with NOT gates. Okay. and generate 2 drawings, the drawing of the logic gates labeled with the appropriate pin numbers. Okay, so what we have not looked at yet is the data sheet for the NOT gate. So let's get that. And that one was, I think it's 11. Nope.
Is it 4?
Oh, you're right, it's 4. By the way, if you ever need to know what they are, if you're in the lab and you need to know, it's there's in that same lab resources folder, there's a page that has a list of all the chips that are in the lab and what they are. Okay, so 4. So the way this one works is pin 1 is an input and pin 2 is the output. So if I put an input into 1, then the output is the NOT of that. And an input into 3, then 4 is the NOT of that. So just to have handy. That is my NOT, and this was uh, 74x04. By the way, the X just stands for everything in the middle between 74 and the last couple digits. So yours say 74LS04, that has to do with the shape of the pin. And so whenever you see X, don't worry about, I can't find X. I have, there's 74LS04, but not 74X04. The X just stands for any of those. So this is 74LS04 or not. And where did I have my OR gate? There it is. And then if you look at the way this is set up, you put the letter, or like the A or the B first, and then you put in parentheses what pin it is. And this one, the example has, if you look at the example, it has 2 AND gates, and it has 2 NOT gates, and it has 1 OR gate. And so it's saying that the number on the gate is corresponding to the number that you're using on the chip, because the chip has more than one OR gate on it or more than one AND gate on it. So for instance, on ours, we could say, I'll make this one 1 and this one 2, and I'll make this one 1 and this one 2. So that means that since this is the NOT gate, I'm coming into 1A, and that is pin 1. When I come out, that's actually this one over here. When I come out, I'm at 1Y, and that's pin 2. For this NOT gate, 2A is pin 3, and when I come out, I'm at 2Y, which is pin 4. And then I come to my OR gate, and I have this one I'm using gate 1, so when I come in, I'm going to 1A, which is pin 1, and my other input is going to go into 1B, which is pin 2, and my output is going to be 1Y, which is pin 3. And then my output from this is going to be an input for my next OR gate, and so this is going to go into 2A, which is pin 4, and the NOT of C is going to go into 2B, which is pin 5, and my output is going to be 2Y at pin 6. So that's the first kind of drawing you're going to create. The second kind of drawing you're going to create is going to be the one that actually shows how you're going to put the chips in. And so you're going to have your switches, and you're going to have VCC, and you'll have ground, and you'll show how they're set up. So we're going to do that. Okay, so we are not using this one. Okay, so I have ground, and ground, I should just label it there. Ground always goes into pin 7, and I have VCC, which you typically do that in red, but if you don't have colors, that's fine. That goes into 14. And then I have A, B, and C. And now I can just read off my other map where they're going into. So A was going into pin 1 of the NOT gate, and C was going into pin 3 of the NOT gate. And then the output of that NOT gate, which was pin 2, was going into pin 1 of the OR gate. And then B was going into pin 2 of the OR gate. And then I believe the output of that OR gate. Oh, did I do this right? Did I do what I was supposed to do? Yeah, I did what I was supposed to do. The output of that OR gate goes into the input of another OR gate. So the output of that OR gate, which was pin 3, went into pin 4 of the other of the next OR gate, so that went into pin 4, and pin 4 of the NOT gate went to pin 5 of the OR gate. I am so glad that I'm a teaching assistant and not a grading teaching assistant. Can you imagine trying to grade these things? No.
Who grades them?
Other grad students. So there are more than one. So there's the TAs. The TA that is in your lab with you is going to be the one who grades your labs, and then there's another TA who grades your homework and tests. And then finally, my output was pin 6 of the OR gate. And that goes to some light. But I can just say Y here. And if you're thinking, well, no one ever showed me how to do this, they never show anyone how to do this. This is always, you're supposed to figure it out from the lab handout. So, but now someone showed you how to do it. Okay, so let's see. And that was the end of Lab 0. So were there other questions on Lab 0? Do you need me to go back and tell some?
Can you show part A again?
Part A, what was part A? The diagram?
Yeah.
Well, first, does anybody need more time on this one?
Actually, yeah, can I get one?
Yeah, yeah. I probably should have actually picked something different than the OR gate, because the OR gate is going to be actually way too similar to y'all's. But, well. Oh, I didn't give out any prizes yet. Let's see. Who can tell me, and I don't need exact numbers, but just basic description of what ground and VCC refer to? And you can have a prize just for answering. You don't have to get it right.
Well, I mean, in this context, grounding probably refers to either the battery that's out, like the line carrying the electricity back to the either the battery or I guess literally to the outlet.
Okay, that's almost exactly backwards, but you're very much you're on the right track. So you can help yourself to a Halloween candy. Anyone else want to help yourself? Anyone else want to give it a shot?
Is the VCC essentially just a power supply?
The VCC is the power supply. The VCC is basically the battery or the power supply, and ground is low voltage. It's 0, so it's no electricity. Yeah, so it's the ground, literally the outlet. The grounding outlet is attached to the ground. Oh,
Thank you.
you can get that in. All right, now I'll go back to part A, and then we'll go into B. And if you need to see anything else again, I do have office hours right after this session, so you can just hang out and ask me then. So there's that. So the numbers on the gates themselves, so like this one is the same as the numbers here. And then my other, the other NOT gate, which is 2, means it's using these. That's, yeah. And then for the OR gate, I have A, B, and Y. So for the OR gate, that would be A, B, and Y for 1. That'd be 1. And then two, 2A, 2B, 2Y, 2A, 2B, 2Y. And that's how I knew where the wires went on the next page where I did the other diagram. Any questions on that? Okay, so I'm going to stop my recording and then start a new recording for the going over